You are floating now, weightless in the profound darkness, and above you, impassably, achingly above you, stretches a river of light so vast it takes your breath away. The stars are so thick they seem almost within reach, and you can feel the gentle cold of space against your skin, a coolness that is somehow not frightening but deeply, peacefully stillness. Around you, vast sweeping arms of light curve and bend with such perfect grace that you wonder if you are witnessing something alive, something that has always been dancing through the void in patterns too intricate for mortal eyes to fully comprehend. The silence is complete, and in that silence lives a profound order. And so our journey begins not with equations or theories, but with looking upward into the night, the way humans have always done, searching for meaning in the points of light scattered across the darkness above. For thousands of years, people gazed at the stars and saw patterns, stories written in luminescence across the black canvas of eternity. They watched the Milky Way wheel slowly across the seasons, a great arc of silver dust stretching from horizon to horizon, and they sensed, though they could not yet articulate it, that there was a structure to this vast display, an architecture beneath the apparent chaos. It was not until the 20th century that we truly understood what we were seeing. In 1924, a photograph taken through the world's most powerful telescope revealed something extraordinary. The Andromeda galaxy, long thought to be a nebula within our own galaxy, was actually an island universe unto itself, containing nearly 1 trillion stars arranged in a shape that caught the observer's eye immediately. The shape was a spiral. Not a simple spin, not a random scatter, but a graceful, geometric spiral that seemed to suggest intention, design, mathematics itself made visible in light years and stellar masses. Across the following decades, as telescopes grew more powerful and photographic technology improved, astronomers began to notice that this spiral pattern was not unique to Andromeda. Nearly every large galaxy they observed possessed this same fundamental structure, vast spiral arms extending from a glowing central core, rotating slowly through space like a celestial whirlpool. The Milky Way itself, we learned, contained approximately 100 billion stars, and these stars were not distributed randomly throughout space, but rather arranged in 2 major spiral arms and several minor ones, creating a shape of breathtaking regularity and elegance. What fascinated scientists most profoundly was not merely that these spirals existed, but that they followed mathematical laws, geometric principles that suggested something deeper than mere chance or random arrangement. The spirals were not perfect circles, nor were they simple unfurling lines. They were something more subtle, more sophisticated. They were logarithmic spirals, mathematical curves that maintain the same angle as they curve outward, the same proportions whether viewed from near or impassably far away, a pattern that repeats itself at every scale. In order to understand these spirals truly, we must venture briefly into the landscape of pure mathematics, though we need not fear it, for mathematics is simply the language in which nature speaks her deepest truths. A logarithmic spiral is a curve that emerges naturally from a simple rule. A point moving along this spiral maintains a constant angle, let us say 70 degrees or 73 degrees or any other fixed angle, between its forward direction and a radial line drawn from the spiral's center outward. This means that as the spiral unfolds, it never tightens. A circle, by contrast, maintains a fixed distance from its center. An Archimedean spiral, named for the ancient Greek mathematician, maintains a fixed distance between successive loops, like the groove in a vinyl record or the arrangement of rope coiled on a ship's deck. But a logarithmic spiral is different. It grows outward at an accelerating rate, and each complete revolution carries you further from the center in the same proportional manner that every other revolution has done. To visualize this, consider a point starting at the center and beginning to move outward while simultaneously rotating around that center. If it rotates 360 degrees and returns to its original angle, It will have moved not to where it started, but to a new distance from center that is some constant multiple of its previous distance. If that multiple is 1.6 times larger after each full rotation, then after 10 complete revolutions, it will be 1.6 raised to the 10th power, roughly 100 times farther from the center. This is the essence of the logarithmic spiral's nature, exponential growth married to geometric rotation. The term logarithmic itself comes from the mathematics underlying this growth. When you take the logarithm of exponential growth, you transform it into a linear relationship, a straight line. Thus, a logarithmic spiral, when graphed on a special kind of paper where distances from center are measured logarithmically rather than linearly, appears as a perfect straight line. This elegant transformation reveals the hidden geometry. What looks curved and complex to our eye is actually profoundly, beautifully simple beneath the surface. Many spiral galaxies follow this mathematical law so precisely that when astrophysicists measure them, they find spiral arms that match logarithmic spiral curves to within remarkable accuracy. The great spiral arms of Andromeda, the sweeping curves of the Sombrero Galaxy, the magnificent spirals of galaxies like M51, the Whirlpool Galaxy, all of these trace out logarithmic spirals as though drawn by an invisible geometric compass rotating across billions of miles of space. Now gently we arrive at a number that has enchanted mathematicians, artists, architects, and nature lovers for millennia, a number so elegant, so perfectly balanced that it seems to embody beauty itself. This number is approximately 1.618, and it is known by many names: the golden ratio, the divine proportion phi, the golden mean. Some call it the most beautiful number that exists, and as we shall discover, this number appears again and again in nature, as though it were a signature written by creation itself. The golden ratio emerges most naturally from a simple geometric problem. If you divide a line into two segments such that the ratio of the whole line to the longer segment equals the ratio of the longer segment to the shorter segment, you have found the golden ratio. This is not a random property of arbitrary lines, but rather a relationship that contains within itself a profound symmetry. Take a rectangle with sides in the ratio 1.618 to 1, and it will possess an unusual property. If you remove a square from one end, the remaining rectangle has the same proportions as the original. This creates a kind of recursive perfection, a shape that contains itself infinitely. The golden ratio is intimately connected to a sequence of numbers that has captivated humanity since medieval times. The Fibonacci sequence, which begins 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, and continues onward infinitely. Each number in this sequence is the sum of the two numbers that precede it. This humble arithmetic rule, first described by Leonardo Fibonacci in the year 1202, in a book about merchant mathematics and rabbit breeding problems, generates a sequence with extraordinary properties. What emerges from the Fibonacci sequence is this: as you move further and further along the sequence, taking each number and dividing it by the number that comes before it, you get closer and closer to the golden ratio. The ratio of 3 to 2 is 1.5, the ratio of 5 to 3 is 1.667, the ratio of 13 to 8 is 1.625, the ratio of 144 to 89 is 1.618. The ratio of 10,946 to 6765 is 1.6180339. With each step, you approach the golden ratio more precisely, forever drawing near but never quite arriving, asymptotically converging toward mathematical perfection. And here is where the spiral galaxies reveal their deepest secret: the angle that logarithmic spirals must maintain to grow in the most efficient manner possible, the angle that minimizes stress and maximizes stability, the angle that nature seemingly selects again and again throughout creation, is directly related to the golden ratio. When you construct a logarithmic spiral that spirals outward by a factor of the golden ratio with each quarter turn, you create what is called a golden spiral, and this spiral matches the shapes observed in galaxies with remarkable precision. And so we learn that what appears in the heavens, in vast structures of 100 billion stars spiraling through space, appears also in the smallest structures that grace our world, as though nature employed a single master blueprint, scaling it up and down but never varying its essential geometry. The chambered nautilus, a creature dwelling in tropical oceans at depths where light barely penetrates, constructs a shell of extraordinary beauty and mathematical precision. And this shell is a logarithmic spiral, so perfect it served as an inspiration to mathematicians and naturalists studying growth patterns. The nautilus begins life as a tiny creature, and it constructs its shell gradually, one chamber at a time. As the creature grows, it secretes new shell material, always in the same proportions, always maintaining the same shape relative to what came before. The result is that each new chamber is approximately 1.6 times larger than the previous one, creating a series of spiral curves that together form a perfect logarithmic spiral. If you measure a cross-section of a nautilus shell and draw a line from the center outward, you find that it intersects each spiral curve at exactly the same angle, consistently, repeatedly, maintaining the mathematical law of the logarithmic spiral. This is not coincidence or statistical approximation. This is nature implementing mathematics with the precision of an engineer. The nautilus does not calculate angles or ratios. It simply grows according to internal instructions encoded in its biology, and yet the result is perfect geometry. The creature grows 1.6 times larger, rotates slightly, grows 1.6 times larger again, rotates slightly again, and layer upon layer, generation after generation, the spiral builds itself, a three-dimensional expression of the Fibonacci sequence and the golden ratio. Spiral shells are not limited to the nautilus. The whelk, a marine snail, builds a spiral shell that follows these same mathematical laws. The shell of the ammonite, an extinct cephalopod that lived for nearly 300 million years before vanishing 66 million years ago, traces out a perfect logarithmic spiral, preserved now in fossils for us to admire and measure. Countless other mollusk shells exhibit this same principle, suggesting that the mathematics of spiral construction is somehow fundamental to how organisms grow and maintain their proportions as they enlarge. What becomes clear is that the logarithmic spiral is not merely a pattern that appears sometimes in nature, but rather an optimal solution to the problem of growth itself. If you wish to grow while maintaining your shape, that is, if you wish to become larger while remaining proportionally the same, the logarithmic spiral is the way to do it. A creature that grows in constant proportion expands outward and upward in a spiral pattern, each new addition the same relative size as what came before. This principle applies whether the creature is a microscopic shell-building organism or a galaxy containing billions of stars. Moving from the ocean depths to terrestrial gardens and meadows, we discover that the spiral pattern appears again, inscribed this time not in the mineral substance of shells, but in the living geometry of plants themselves. The sunflower, with its striking yellow petals and dark center, has long been recognized as a symbol of mathematical beauty, and rightly so. At the heart of a sunflower bloom lies an arrangement of seeds that demonstrates the Fibonacci sequence and the golden ratio with astonishing clarity. In a sunflower's center, hundreds or even thousands of seeds are arranged in a spiral pattern, and if you count them carefully, moving outward from the center, you will find concentric spirals running in one direction and other spirals running in the opposite direction, and the number of spirals in each direction will be consecutive Fibonacci numbers. One flower might possess 21 spirals in one direction and 34 in the opposite direction. Another might show 34 and 55 or 55 and 89. These are not random numbers, they are consecutive values from the Fibonacci sequence. The reason for this arrangement is efficiency. The sunflower must pack as many seeds as possible into the center, Each seed must receive adequate space and light for proper development, and the arrangement must allow for seeds to grow to maturity without crowding their neighbors. The optimal solution to this packing problem, the way to distribute the maximum number of objects in a spiral while maintaining uniform spacing, is to place each new seed at an angle of approximately 137.5 degrees from the previous seed. This angle, known as the golden angle, derives directly from the golden ratio and emerges naturally when attempting to arrange objects in optimal spirals. The golden angle is calculated as follows. The golden ratio is approximately 1.618, and if you take 360 degrees, a full circle, and divide it in the golden ratio, you obtain approximately 222.5 degrees for the larger section and 137.5 degrees for the smaller section. This 137.5 degree angle is the golden angle, and it is the perfect rotation rate for packing seeds in spirals. Rotate 137.5 degrees and place a seed, rotate another 137.5 degrees and place another seed. Continue this process thousands of times, and the seeds naturally arrange themselves in beautiful spirals with consecutive Fibonacci numbers in each direction. This same principle appears throughout the plant world. The spiral arrangement of leaves on a stem called phyllotaxis follows Fibonacci patterns. The arrangement of petals on flowers frequently follows these principles. The construction of pine cones reveals spiral patterns with Fibonacci numbers. In ferns, the arrangement of leaflets along the rachis, the central spine of each frond, traces out these patterns. Even the branching structure of trees itself, as it divides and subdivides, often follows the mathematical rules encoded in the Fibonacci sequence, each branch splitting in a way that optimizes light capture and structural stability. What emerges from studying these natural arrangements is a profound realization. The golden ratio and Fibonacci sequence are not arbitrary mathematical abstractions, but rather practical solutions to real biological problems. A plant that arranges its seeds or leaves according to these patterns will receive more sunlight, will disperse its seeds more effectively, will achieve greater stability and strength. Nature, through countless generations of growth and selection, has discovered that the mathematics of the golden ratio and Fibonacci sequence are optimal solutions, and it implements these solutions with the precision of a master architect. As we venture further into the natural world, we encounter the spiral in places where we might least expect it, in the vast atmospheric systems that shape weather patterns across our planet. The hurricane, that terrible and awesome phenomenon of rotating winds and torrential rain, forms a spiral of water and air so large it can be observed from space, spanning sometimes hundreds of kilometers across. When viewed from above by satellites, these storms display a spiral structure that is unmistakable, a clear mathematical form imposed on chaotic atmospheric conditions. A hurricane develops when warm, moist air rises rapidly from the surface of the ocean, and as it rises, the Coriolis effect, a consequence of Earth's rotation, causes the rising air to rotate. More and more air is drawn into this circulation, and as the system intensifies, the spiral becomes more tightly wound, more pronounced, more geometrically regular. The spiral structure of a hurricane is not random, but follows principles of fluid dynamics and atmospheric physics, creating a shape that mathematics can predict and describe. The spiral is an efficient way for energy to organize itself in a rotating fluid. As the hurricane spirals inward toward its center, wind speeds increase dramatically, following laws of conservation of angular momentum, the same principle that makes a figure skater spin faster when pulling their arms inward. The spiral arms of a hurricane are logarithmic spirals, mathematical curves that emerge naturally from the equations governing fluid motion on a rotating body. Typhoons, cyclones, and all the great rotating storm systems of Earth follow this same principle. Whether in the Atlantic or Pacific, in the Indian Ocean or the South China Sea, when atmospheric conditions are right, the forming storm system naturally spirals into logarithmic curves. The spiral is not imposed from outside, but emerges from the fundamental laws of physics, from the way rotation and expansion interact when governed by conservation laws and boundary conditions. Tornadoes, those violent vertical vortices, similarly display spiral structure, though their spirals are tighter and more intense. The dust devil, a small whirlwind that forms when hot air rises from sun-baked ground, traces out a miniature spiral, a smaller expression of the same mathematical principle. Even whirlpools and waterspouts, the spirals formed by water in motion around a central axis, demonstrate the same logarithmic geometry. The spiral is nature's solution to rotation, the way that circular motion naturally manifests when physical laws are applied to large-scale systems. And so gradually through our journey, a deeper understanding emerges. The spiral, the golden ratio, the Fibonacci sequence, these are not merely decorative patterns scattered through nature like jewels in a garden. Rather, they are intimately connected to the fundamental process of growth itself, to the way that living things enlarge while maintaining their essential character and proportions. To grow while staying the same shape is to spiral outward, and the most efficient spiral is the logarithmic spiral, which maintains constant angles as it expands. This principle applies at every scale of biological organization. A single cell dividing into two cells dividing into four into 8. The exponential growth pattern seen in cell division is related to the same mathematical principles that govern the spiral. The branching patterns of blood vessels in your body, carrying nutrients and oxygen to every tissue, follow branching rules that often reflect Fibonacci proportions. The branching of your bronchial tubes as they descend into your lungs, dividing and subdividing until they reach the tiny air sacs where oxygen enters your blood, reflects these same mathematical patterns. The spiral appears in the double helix of DNA itself, the molecule of life that carries genetic information in every living cell. This is perhaps the most profound spiral in nature, for contained within its graceful curves are the instructions for building organisms, including humans. The DNA double helix is not a spiral in the mathematical sense of a logarithmic spiral, but rather a different kind of helix, a regular spiral that completes one full rotation every 3.4 nanometers along its length. Yet even in this structure, we see spiraling as a fundamental organizational principle of life. From the molecular to the cosmic, from DNA to galaxies, the spiral appears as nature's favorite pattern. This is because the spiral is inherently connected to growth, rotation, and the way that expanding systems naturally organize themselves. An expanding system that rotates will spiral. A growing organism that adds new material proportionally will spiral outward. A rotating fluid that expands will form spiral structures. The spiral is not a choice, but a consequence, not a design, but an inevitability that emerges from the laws of mathematics and physics. What this reveals is that the order we observe in nature is not imposed from without, but arises from within, from the fundamental properties of growth and rotation and proportion. When conditions are right, when energy and matter are available, and when time allows for development, the result is spirals. The universe does not seem to require a designer to create these patterns. The patterns create themselves, following mathematical laws as inexorably as water flows downhill. To understand the spiral fully is to understand something profound about how we perceive the world and how the world itself is structured. The spiral is visible across scales of magnitude that our minds struggle to encompass. A galaxy containing billions of stars spirals through space, taking tens of millions of years to complete a single rotation. And yet this vast spiral follows the same mathematical laws as a sunflower seed arrangement that can be viewed and measured in moments, or a seashell spiral that can be held in the palm of your hand. This scaling property, where the same pattern repeats at every size and magnitude, is known as self-similarity, and it is characteristic of logarithmic spirals and other fractal patterns. When you zoom in on a logarithmic spiral, magnifying your view by a factor of 100 or 1000, the pattern you see looks virtually identical to the pattern at larger scales. The same curve structure appears at every magnification, a property that no finite geometric shape possesses. A circle viewed very closely looks like a straight line, but a logarithmic spiral remains a spiral no matter how closely you examine it. This property has a strange and wonderful consequence for perception. When we observe spirals in nature, we are, in a sense, observing the same pattern repeated across all of creation. The human eye perceives spiral patterns readily. We are drawn to them, find them beautiful, even find them calming. There may be deep evolutionary reasons for this. Our ancestors lived on a planet where spirals appeared in shells and plants, and those who found such patterns beautiful, who were drawn to them and found them organizing principles in nature, may have been more successful in understanding their environment and adapting to it. The appreciation of spiral patterns may be written into our neurology, encoded in the way our brains process visual information. Spirals have a certain dynamism to them. They seem to move even when still, seem to pull your eye inward or outward, seem to suggest motion and growth and the passage of time. Perhaps our visual system, having evolved on a planet rich with spirals, finds them particularly compelling and beautiful. To observe a spiral is to see a pattern that has shaped the evolution of life itself, and to recognize this is to feel connected to something vast and ancient. As we continue our gentle exploration, we arrive at a contemplation that many have found profoundly peaceful, that beneath the apparent chaos and randomness of the natural world lies hidden order, mathematical precision, patterns that suggest, though we need not insist on interpretation, that the universe is not a meaningless accident, but rather a system of profound and elegant organization. The discovery that a spiral galaxy and a sunflower seed arrangement follow the same mathematical law, that a hurricane and a nautilus shell obey the same geometric principles, is a discovery that brings with it a sense of peace and unity. In the early part of the 20th century, when astronomers and mathematicians were making these discoveries, there was widespread wonder at the implications. How could nature, operating at such vastly different scales and with such apparently different materials and conditions, generate the same patterns? How could the same ratio, 1/618, appear in the spirals of galaxies and the seeds of flowers? What principle governed this universal occurrence of the Fibonacci sequence? Modern physics and mathematics suggest that the answers lie in optimization and efficiency. The mathematical patterns we observe in nature emerge because they are optimal solutions to real problems. How to pack seeds efficiently, how to grow while maintaining proportion, how to rotate and expand while maintaining stability. Natural selection, operating over millions of years, tends to favor organisms that solve these problems well, and organisms that grow according to golden ratio proportions and Fibonacci patterns survive and reproduce more successfully than those that do not. Yet even with this understanding, there remains something wonderful, something that resonates deeply in the human spirit. The fact that these patterns are optimal, that they are discovered rather than invented, makes them no less beautiful. A mathematical theorem is no less elegant for being true. A natural pattern is no less wonderful for having a logical explanation. Indeed, understanding the principles behind the patterns deepens the appreciation, for it reveals the necessity and inevitability of the forms we observe. This brings great peace to many people. In a universe that can sometimes seem random, indifferent, and chaotic, the discovery of hidden mathematical order is reassuring. It suggests that the universe operates according to intelligible principles, that there is a deep rationality underlying the apparent complexity. When we observe a spiral, any spiral in a galaxy or a shell or a flower, we are observing the universe speaking its own language, mathematics expressing itself in form and matter. To learn to read this language is to feel less alone in the cosmos. And finally, we arrive at perhaps the most humbling consideration, that the spirals we observe in nature are not merely spatial patterns, existing across great distances, but are also temporal patterns, spirals unfolding through time itself. The spiral galaxy does not spiral for a moment and then remain stationary. Rather, it rotates continuously, taking hundreds of millions of years to complete a single rotation, with individual stars within the spiral taking their own time to orbit. As a galaxy rotates, the stars within it are not carried along rigidly, like points painted on a turning wheel. Rather, the spiral pattern itself persists while individual stars flow through it like water flowing through a channel, a phenomenon known as the density wave theory. The spiral arms of a galaxy are not permanent but are regions of slightly higher density, where stars crowd together more closely for a time before flowing onward. A star entering a spiral arm might spend millions of years within it, experiencing gravitational forces that compress its local neighborhood, triggering star formation, before eventually flowing out the other side. The spiral pattern persists across the rotation of stars, like a wave in an ocean that maintains its form while water flows through it. This temporal dimension adds a profound layer of complexity to our appreciation of spirals. A spiral galaxy is not a static snapshot but a dynamic pattern, continuously rotating, continuously processing stars and gases and matter through its spirals, continuously creating new stars and light in the regions where its spirals compress the galactic disk. The spiral we observe in a photograph is merely one instant in an ongoing process that has been unfolding for billions of years and will continue unfolding for billions of years more. Our own Milky Way, containing our Sun and 100 billion other stars, has been spiraling for some 13.6 billion years, since near the beginning of the universe itself. Our Sun, burning in its core the hydrogen that was forged in the first few minutes after the Big Bang, orbits within this spiral, completing one full orbit every 225 to 250 million years. In the time since the dinosaurs went extinct 66 million years ago, the Sun has completed a small fraction of its orbit. The last time our solar system was at its current position in the Milky Way's spiral, the ancestors of humans had not yet diverged from their common primate relatives. This perspective, contemplating spiral motion across billions of years and billions of kilometers, brings home the vast scales at which the universe operates and the tiny place our own existence occupies within those scales. And yet, by understanding the mathematics of spirals, by recognizing the same patterns in a galaxy and in a seed, we connect ourselves to those vast scales. The same principles that govern the rotation of galaxies govern the arrangement of our own atoms. We are made from the matter that has spiraled through the Milky Way, and the oxygen in our blood was likely forged in the cores of stars that spiraled through the galaxy far before our Sun even existed. And so, as our journey through the realm of spirals gradually draws to a close, we find ourselves standing at the intersection of mathematics and wonder, of precision and beauty, of vast cosmic scales and intimate cellular dimensions. The spiral we have discovered is not merely a shape but a principle, not merely a pattern but a fundamental expression of how growth and rotation and expansion naturally occur in a universe governed by mathematics and physics. The sunflower turning its face through the days, following the sun's arc across the sky, holds within its structure the same mathematical constants that govern the rotation of galaxies containing billions of stars. The nautilus, dwelling in the quiet depths of the ocean, builds its shell according to the same geometric principles that structure the spiraling arms we observe through telescopes pointing toward distant galaxies. A hurricane, forming in the warm waters of the tropics, spontaneously organizes itself into the same spiraling pattern that appears in flower seeds and seashells and DNA. This unity underlying apparent diversity, this order beneath the surface of seeming chaos, has inspired human thought for countless centuries. Mathematicians have pursued these patterns, finding beauty in their structure. Artists have incorporated spirals into their work, recognizing their aesthetic power. Philosophers have pondered the implications, wondering what it means that such patterns repeat across all of nature. And perhaps most importantly, those who simply pause to observe, to look closely at a shell, to watch a spiral galaxy through a telescope, to note the arrangement of petals on a flower, have experienced that particular kind of peace that comes from recognizing order, from feeling, however briefly, that the universe is not random but comprehensible. As you rest now, letting your consciousness drift downward into the peaceful realms of sleep, you might hold this image in your mind. A spiral, any spiral expanding gracefully outward, each curve the same proportional distance from the last, each rotation carrying you further into the infinity of pattern. Hold this image not as an intellectual exercise, but as a feeling, a gentle sense of movement, of growth, of order unfolding. The mathematics is there, real and true and underlying everything, but you need not think of equations now. Simply rest in the knowledge that you are part of a universe structured according to elegant principles, that the same curves that shape galaxies shape seeds and shells and the very spirals of wind and water. The Fibonacci numbers continue infinitely onward, each one the sum of the two before, and the golden ratio continues to exist everywhere and nowhere, present in the proportions you perceive without ever quite reaching them, forever approached but never quite attained. Let your mind spiral gently downward now through layers of thought and consciousness toward the peaceful rest that awaits. The universe spirals, all of nature spirals, and in spiraling it finds its order, its grace, its endless beauty. Sleep now deeply and peacefully, cradled by the knowledge that you exist within a cosmos of infinite pattern and subtle mathematics, where the smallest shell holds the secrets of the largest galaxy, where growth follows rules as elegant as they are invisible, where spirals unfold at every scale, from the unimaginably vast to the intimately small, all of it beautiful, all of it connected, all of it continuing its slow dance through the darkness of space and time. And, word count, 5,487 words.